In this video, we're going to be taking a look at a projectile that's traveling horizontally and then falling onto a decline. Now, the first thing we're going to do is take this 30 degrees and we're able to translate it over here, and then we can make ourselves a little 90-degree triangle. And then from there, we have a few different things to do. We're going to go ahead and analyze everything in the x direction first. So in the x direction, we're going to be using this formula right here because there are no forces in the horizontal direction, which makes it a constant velocity. So we're going to use v equals delta x over t. Now, we know that the velocity is going to be the 10 meters per second because all of it's directed horizontally. And then other than that, we actually don't know much from there. So we can say that 10 equals delta x over t. And then if we want to solve for t, then we can go ahead and put on this side and we can call it delta x over 10. And that's going to be a helpful substitution for us a little bit later down the road. Now, the second thing we're going to do is analyze stuff in the vertical direction. So in the vertical direction, the only thing we know is that the initial velocity is 0 meters per second because it has no velocity directed straight up or down. And there is an acceleration in the vertical direction because of gravity, which is always negative 9.8 meters per second squared. Other than that, we're pretty slim on variables there. Now, what we're going to do is we're going to use this second formula over here and plug in some values, and we would have delta y equals VIT, which is going to be 0. So actually, we don't even need that whole entire beginning part, times 1/2 negative 9.8, and then t squared. So we have too many unknowns, so we're going to use a little system of equations and do some substitutions and things like that. And one thing that we have to do is we have to see the relationship between our delta y and our delta x. So what we can do is draw like a little triangle on the side, and the relationship between our delta y and our delta x is going to be related to the tangent of the angle. The reason why it's tangent is because tangent takes the opposite side and the adjacent side. So we know that the tangent of 30 degrees equals our delta y over our delta x. So we know that if this 30-degree angle is involved, that proportionality-wise, that the tangent of 30 degrees times our delta x, if we multiply both sides by this delta x, equals our delta y. So we're going to have to do that so that we can put everything in terms of delta x, and then we can go ahead and use that to help find our final answer. So we are going to make this substitution in right over here for this delta y. So we have the tangent of 30 degrees times delta x. And then also we have 1/2 times negative 9.8, which is negative 4.9. And then for t squared, we're going to grab this setup over here, and then we're going to have everything squared. So delta x squared, and then 100, or excuse me, 10 squared is 100. All right, now that's looking pretty good because we have only one unknown, which is our delta x. So what we can do is divide both sides by delta x, and that gets rid of it on this side, and then gets rid of that squared value there. And then we have tangent of theta on this side. And then we have negative 4.9 divided by 100, which is negative 0.049 times delta x. Okay, and then what happens here is I actually forgot one negative sign in here. Because this delta y that we solved for earlier is a negative delta y, because the object is dropping. So it actually includes a little negative sign over here. which is going to be placed right up here, which is going to drop down there. So I forgot that negative sign a little bit earlier. So that one's kind of important because now when we divide both sides by negative 0.049, then the negative is going to drop out. Okay, so it's basically our tangent of theta, which is 30 degrees. I forgot to write 30 degrees in there. Divided by negative 0.049, and then that equals our delta x. So our delta x is equal to 11.78 meters. Okay, now that isn't our final answer because we're looking for where the object is going to fall and land on our decline. But we do have the x portion of our triangle. So if it looks like this, there is our x component. There's our decline right here. We'll just see d for distance or d for decline, doesn't really matter. And then there's that 30-degree angle that's right over here. Okay, so if we want to see where it's going to land on this, it's basically the hypotenuse of that triangle. So what we can do is use the adjacent and hypotenuse side, which is cosine. So that means we have the cosine of 30 degrees equals adjacent 11.78 over that hypotenuse of distance d. We can go ahead and cross multiply those two, and 11.78 divided by the cosine of 30 gives us that distance on the slope, which is about 13.660 meters. So to solve this kind of problem, you want to make sure you have a pretty strong basis as far as projectile and free fall concepts go. From there, you're going to want to solve for t in terms of delta x, and then you're going to want to have your vertical set up over here and have everything in terms of delta x with a couple substitutions that we had in this green box over here and this orange box we subbed into this formula over here so that we could find delta x. And once we have one part of our triangle and an angle, we are good to find another part of our triangle, which is eventually the hypotenuse that was our actual slope there. That led us to our answer of 13.60 meters. I hope that was helpful to you. Thank you for watching and listening.